All right, so yesterday we talked about Lewis dot structures. We'll do a little bit of warm-up today just to get some practice under our belt. So I'm going to give you guys 3 different Lewis structures to take a look at, and I want you to not only draw them out, but determine the charge as well. So let's do some warm-up. The first one we're going to do is Al, so that's aluminum, not iodine, and then H4. The question is, what charge does this have, and where is the charge located? For number 2, we'll look at Cn, and again, we'll have to determine what charge we have and which atom that charge is located on. And then for the last one, we're going to do a little bit harder one. We'll do BnH6, and again, we need to determine where the charge is. So I'll give you guys a minute to work on this, but remember, the first thing you want to do is take a look at the periodic table, determine the valence number, try to connect things together, and then add and remove electrons as needed. If you add an electron, there will be a negative charge on that atom. If you remove it, there will be a positive charge. Once you think you've got it, check with the neighbor too and see if you guys are coming up with the same drawings. Show of hands, how many people think they've got it? All right, so it looks like about half the class. Let's just go through them one at a time. I don't mean to rush you guys, but we do have a pretty full class period. So aluminum, how many valence electrons? 3. So we'll do dot, dot, dot. We've got 4 hydrogens, so I'll do a hydrogen here, 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 and here. Hydrogen has how many? 1. So we've got 1 there, 1 there, 1 there, 1 there. Can we form bonds between this aluminum and hydrogen? Yeah, it's a shared pair, shared pair, shared pair. What about that top hydrogen? No, we've got to get another electron here, right? So we're going to take this electron, we're going to shove it into this spot right there and form a new bonding set. If we do that, what charge will the aluminum have?
Negative.
Negative. So if we do this, we can erase this, draw a bond, and then aluminum has a negative charge. You'll notice I tend to circle my negative and positive charges just to ensure that people know that it's not a plus sign, meaning we're not adding 2 things together. That's the formal charge. So aluminum has a negative charge here. The net charge is -1. If we do carbon and nitrogen, we've got carbon that has 4 valence electrons, nitrogen has 5. That looks pretty good. So immediately we can say, well, let's pair up those 2 electrons as a covalent bond. Then we can pair up these 2 electrons as a covalent bond. And we can do these 2 electrons as a covalent bond, right? So it looks like we could have a triple bond between those. That doesn't violate anything. What about that carbon?
You could add an electron to get the lone pair.
Yeah, we need to add an electron. We know electrons tend to be paired. This carbon, if we look at it right now, isn't following the octet rule. It needs 1 more electron. The nitrogen, on the other hand, is fine. So if we were to look at this and draw it out nicely, I'm going to erase it. We could have carbon, triple bond, nitrogen. That nitrogen has a lone pair. This carbon has a lone pair. However, this carbon has a formal negative charge on it. Does that make sense? All right, now the tricky one. We've got BNH6. This is called Ammonia Borane. We'll start with boron. We know boron has typically 3 electrons. 1, 2, 3. And then we've got nitrogen over here that has 5 normally. So I'll go 1, 2, 3, 4, 5. And then we've got 6 hydrogens around it, right? So let's fill in these hydrogens. We've got hydrogen here, lone pair, lone pair. We'll put another hydrogen down here, and then 3 more over here, and then we'll try to connect things up and bond them all together. Okay? Things look a little out of order, but let's just try to connect them together like Lego pieces. You can do covalent bond, covalent bond, covalent bond, covalent bond, covalent bond. What about that nitrogen and hydrogen?
It can move the electron over.
Okay, so let's do this. Let's bond this, but what we're going to do is take this electron and just pluck it out, right? Because we don't need more than that octet. We'll pull it away. So what charge will that nitrogen have?
Positive.
Positive. Perfect. And then if we look at this boron, it can't bond to that hydrogen, right? So what does it need?
An electron.
A new electron, right? So we'll take an electron, we'll put it in there, and now all of a sudden we can form that covalent bond. What charge will boron have now?
Negative.
Negative, okay. So if we look at this new molecule that we've drawn, what charge does it have? 0 overall, right? The positives canceling out the negative. This happens in chemistry once in a while. And there's a very specific term. This is called a Zwitterion. Where it has both a positive and a negative. Zwitterions are neutral, however, they do really unique chemistry because they have formal charges on individual atoms. Conversely, the 2 on the left are just anions. All right, a lot of people I saw during the problem of the day, they drew problem 1 a variety of different ways. I was telling you that that wasn't necessarily right or wrong. Does anybody know the term for 2 different molecules when you draw them differently? Resonance is one way. With resonance, we're moving electrons. We're not moving around atoms. There's another term when you move around atoms.
Isomer.
Isomers, right? So that's what we're going to move on to today is talk about isomers and then the 3-dimensional layout of atoms. So let's start with isomers. Isomers are compounds. Let me erase this. I'll abbreviate compounds just to save time. Actually, I'll write it out. They are compounds that have the same molecular formula but a different spatial layout. If we look at number 2, Sulfur, carbon, and nitrogen have the same layout. All we're doing is moving electrons, so that's an example of resonance. If you're physically moving an atom around to a different portion of a molecule, that would be an example of an isomer. So let's take an example of an isomer. There's two different isomers for this molecular formula. I want you guys to see if you can come up with both of them and then draw the Lewis dot structure. See if I can get this working. Looks like my pen's freezing up, but it's C2H6O. And see if you can come up with both isomers for C2H6O. And then draw the Lewis dot structure. Yep.
Could you pop up the definition?
Yeah.
Should I be a T? Spatial.
For which one?
Spatial.
Is it TIAL? I don't know.
Good speller.
Yeah.
Myself.
How do you spell it? Oh, shoot. Is that right?
I think so.
Yeah.
Okay, I'm not an English teacher, so I apologize if I spell
They're
things wrong.
recognizable.
Yeah. Phonetically, I was close.
Pompey had it good.
A good way to tackle Lewis dot structures too is to leave the hydrogens till the very end. Make your backbone and then fill in those gaps with hydrogen. Because you know hydrogen can only make one bond, right? So it's always going to be on the outside. Show of hands, how many people think they got both of them? A few people? All right, let's take a look at it. And just focusing on carbon and oxygen, we'll leave the hydrogens out. One example I could think of is we could have carbon, carbon, oxygen, right? The other one could be carbon, oxygen, carbon, right? So one could have two carbons in a row, the other one could have the oxygen in the middle. We know that carbon likes to form 4 bonds, so we could have 1, 2, 3, 4. This carbon over here could have 1, the carbon next to it is another bond, 3, 4, and then we'll do the same thing over here. All right, we need to fit in 6 hydrogens, so let's fill those. We know we've immediately got 1, 2, 3, 4, 5, and what about the 6th one? On the oxygen. Okay, so we'll put that out here. That oxygen's missing something. What do we need?
2 pairs.
2 lone pairs, right? It doesn't have an octet, so we'll do 2 lone pairs. This is ethanol, everybody's favorite alcohol. If we will look at the one next door, we can fit hydrogens here, 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 and here. And again, in order for the oxygen to have a complete octet, we need 2 lone pairs. So we'll plug those in, and this looks good. Do you think these are going to behave similarly or differently?
Different.
Differently. The one on the left can do something pretty unique.
Drop a hydrogen.
You guys remember from Gen Chem, there's a special type of bonding. It occurs in water. Hydrogen bonding, right? Can the one on the right do hydrogen bonding? No. So if we look at this, ethanol, because it can hydrogen bond, has a boiling point that's relatively high. It's 78 degrees Celsius. Ethanol is very sticky. It sticks to a lot of other ethanol molecules due to this network of hydrogen bonding. The molecule on the right, dimethyl ether, can't hydrogen bond, right? There's no hydrogen coming directly off of that oxygen. So its boiling point will be significantly lower. Its boiling point will be about negative 10 degrees Celsius, meaning if you open this up in this room, it would immediately start boiling and evaporate on you. So very different properties, even though they have the same molecular formula and same molecular weight. That's why I really don't like using molecular formulas, right? They don't tell you anything about a molecule. It's a lot better as an organic chemist to draw a molecule out. So from here on out, let's not use molecular formulas. Let's always try to draw the Lewis dot structure or a three-dimensional representation of our molecules. The reason being, isomers often have different physical properties. So we want to draw them out to avoid confusion. Make sense? All right. So let's talk a little bit about Lewis dot structures and how they're not the best way of drawing a molecule. They're a good way, but not the best way. And this has to do with VSEPR theory. How many of you guys remember VSEPR theory? Good chunk of you. All right. So let's take a look at the problem with Lewis dot structures. Let's take a look at methane. So methane is CH4, so a carbon with 4 hydrogens. If we look at this, it looks to me like the angle between those two hydrogens, or any two hydrogens, is going to be roughly 90 degrees, right? So we could say, all right, two-dimensionally, this looks like a 90-degree angle. Is that correct? No, it's not close. If we lived in a two-dimensional world, that would be correct, but we don't live in a two-dimensional world. We have to think about this with some three-dimensionality, right? So instead of drawing it flat, I'm going to do a hydrogen pointed up, a hydrogen pointed here, and then I'll have a hydrogen as a dash and another hydrogen as a wedge. What does the dash mean?
It's the backwards.
Yeah, it can be a little confusing to think about, but chemists like to use dashes to show something going into a board, so it's sticking away from you. A wedge means it's coming out towards you. So we're trying to give it a little bit of perspective. So another way of thinking about this is kind of like a three-legged stool, right? You've got 3 legs sticking down. They're not all on the same plane, and then you're kind of sticking up above it. The ideal angle for methane is 109.5. So this is a much, much better way of drawing out methane. And this is the VSEPR model that we're talking about. The reason that we adopt this conformation is that electrons want to be as far apart from other electrons as possible. So electrons, both bonding and lone pair electrons, want to be as far apart from each other as possible. Another way of saying this is valence. Oh man, this is a mouthful. Valence shell electron pair repulsion theory. If we're using plain English, electrons want to be far apart from one another. The reason behind that is electrons all have that negative charge. Negative charges, if you push them close to one another, repel each other, right? So it's just a repulsion of electrons. And what I did for you guys was I gave you a cool handout. It doesn't look super great on the screen because it's a lot of green. But this is a good review of VSEPR theory and the three-dimensionality. I've got some excellent news for you guys, though. In organic chemistry, we really don't care about these guys. So you can scribble them out for the most part. We might occasionally see them, But these are shapes that you might see in inorganic chemistry. They're not very common in organic chemistry. Those rely on d orbitals. But let's take a look at the top 3 rows. And there's some important terminology I wanted to bring up. The first one is called steric number. So let's make a little note. Steric number is the number of bonded atoms and the number of lone pairs. And if you look at the far left-hand column, it shows you the steric number, right? So if we look at this pink one right there, it's a steric number of 2 because we have 2 bonded atoms, right? This becomes really helpful, especially as you're starting to assign the hybridization of that atom. And we'll talk about hybridization here in a second. So what shape do molecules adopt when they have a steric number of 2? Linear, right? It's just a straight line. That's the furthest apart those electrons can possibly be from one another. The hybridization of this central atom is going to be referred to as sp. And we'll come back to that in a little bit, and I'll explain that in more detail. If we look at a steric number of 3, that's the ones that are in the teal there, you can either have 3 bonded atoms, or you can have a central atom that has 2 bonded atoms and 1 lone pair. If we look at the one with 3 bonded atoms, that's referred to as trigonal planar. And if we look at the one with 2 bonded atoms and a lone pair, that's referred to as bent. Typically, bent configurations are pretty close to 120 degrees. If you have a lone pair, it'll go a little bit out of whack and that angle will be reduced. However, it's a good approximation to know that anytime you've got a steric number of 3, 120 degrees is a good answer. The hybridization for these guys is going to be sp2. Pretty easy to remember. And then the one that's most common in organic chemistry is a steric number of 4. So if we think about methane, that had 4 bonded atoms around carbon, and so that is referred to as tetrahedral, and like I said, that has an angle of 109.5. If you've got 3 bonded atoms and 1 lone pair, that's called trigonal pyramidal, and again, pretty close to 109.5. A lot of people will ask me, do I need to memorize the exact angles, meaning do I need to know 107 degrees? As long as you're ballpark within a couple of degrees, I'm not going to be overly upset. Just try to remember 109.5 for a steric number of 4. If you've got 2 bonded atoms and then 2 sets of lone pairs, that means it's bent. A good example of that would be water. And all of these that have a steric number of 4 are going to be sp3 hybridized. So this should hopefully be a review for you guys. If this looks pretty foreign, I would recommend trying to schedule an appointment with me to talk about it, or just open up your Gen Chem textbook and do a little bit of review. All right. So now what we're going to do is kind of shift gears a little bit and talk about the hybridization. That's going back to the sp, sp2, and sp3. All right, so molecular orbital theory. I think those of you that took Dr. Allen's class got a fair amount of this, right? I'm not sure about the other classes. And atoms? Okay, so we'll jump into this. But if something seems a little rusty, feel free to shoot up a hand and ask me a question. So the first thing I want you to remember from Gen Chem is that electrons fill the lowest to highest energy orbitals. This is referred to as the Aubau principle, if you remember that from Gen Chem. And the easiest way to remember the order from lowest to highest energy orbitals is to make a chart like this, right? So your first row is 1s, and then you've got row 2 below that, and then you go 2s, 2p, and then below that you've got row 3, 3s, 3p, 3d, and then row 4, you've got 4s, 4p, 4d, 4f, and then go on to 5. That's not the absolute order, but it's a good way to get started. A good trick for remembering the absolute order is to fill it in with diagonal lines. So we go like this, like that, like that, like that, like that, like that, that, and that. That means that the order from lowest to highest is we started out at 1s and we went through it. Then the next one would be 2s. And then after that we've got 2p. And then we've got 3s. That was where the arrow went. And then after that we've got 3p, 4s, and you can go on and on and on. But it's important to remember that's the order from lowest to highest energy orbitals. It's easy to forget. The other thing too is in organic chemistry, we're primarily dealing with s and p orbitals. What the heck does an s orbital look like? Sphere, right? All right, so s orbital looks like a sphere, pretty easy to remember. What about a p orbital?
It's the lobe in the middle, and the sphere is kind of like split like a water balloon. Push it in half.
Yeah, it kind of looks like a dumbbell. If you go to the gym and lift dumbbells, that looks kind of like a p lobe, right? With p orbitals, we actually have 3 different types. The way to think about this is with a 3-dimensional coordinate system, right? The first one we can think of, I'll draw this in blue, is one going directly up and down on this y-axis. The next one we can think about could be going along that x-axis. So we'll do the x-axis over here. The node's always going to be in the center there. And then last but not least, we've got our z-axis. So we have 3 different types of p orbitals, or 3 different orientations for them. And it's important to remember that because each one of these p orbitals can hold 2 electrons. So the p set can hold a grand total of 6 possible electrons, right? So let's continue on. And there's one other thing I want you guys to remember from Gen Chem. And that is electrons want to be paired in orbitals, and they want to be paired with an electron that's an opposite spin. If you remember from your Gen Chem textbook, this is the Pauli exclusion principle. So you always want an electron that's spin up paired with an electron that's spin down. We're not going to go into the quantum mechanics behind that. If you go on and take physical chemistry, you'll cover that in a lot more detail. So let's take a couple of examples and we'll try to fill that lowest energy orbital all the way up to the highest energy orbital. So when I do this, what I like to do is make a little energy ladder. Is it okay if I scroll up, or do you guys need more time to copy? A second? Okay. Sorry, sometimes I go fast. Just yell at me if I'm going too fast. All right, so let's take a look at this. I've got an energy ladder, right? We said 1s is going to be the lowest energy one. That'll be the bottom of the ladder. Next up is 2s. And then next up is 2p, but we said that those p orbitals, there's actually 3 different orientations, so we need 3 different steps on that ladder. All right, and I've got 2 of them side by side. For the first one, what I want you to do is to fill in this ladder with the valence electrons for carbon, and then you notice I've got an identical ladder next to it, and we'll fill this with the valence electrons for fluorine. Oh. Sorry, I shouldn't say valence electrons, all the electrons, because the valence electrons will just be the highest energy ones. All right, so carbon, how many electrons do we need? 6 total. There's 4 valence electrons, but 6 if we're starting from the very bottom. So we go 1, 2, should I go 3? No, that violates the spin pairing, right? So we need spin up, spin down. That's 2 of them. Then we've got 3, 4. And then do I go 5 and 6? No, we want to distribute them out evenly before we pair them. So we go 5, 6. So this would be the correct molecular orbital diagram for carbon. Then what about fluorine? How many total electrons? 9. So we can go through and we could say 1, 2, 3, 4, 5, 6, 7. What about the 8th and 9th?
You spin down.
Then we do a spin down, right? So 8 and 9, right? So we can draw molecular orbitals this way. Pretty easy to remember this way. However, the reality is a little bit more complicated than that. So let's first discuss a simple case, and then we'll go into the harder cases. So in simple cases, unpaired electrons in these molecular orbitals will pair with an electron in another molecular orbital. This is really only for simple cases. So let's take a look at the simplest of all cases, hydrogen. So let's take a look at hydrogen. It's plain old H2 gas. We can take a look at our molecular orbital ladder and we can fill it in. So hydrogen, what orbital do we have? 1s. It's really the only one, right? Because hydrogen only has 1 electron. So we can say, all right, if we've got 1 hydrogen atom, it's got 1 electron, and let's draw that hydrogen atom over here. Oop. I'll do it in black. It's got 1 electron, and we'll represent that with a dot. It's in an s orbital, so we'll do kind of like a sphere. If we've got another hydrogen atom over here, this one could also have an electron, and it could be 1s, and there's a probability of that electron being spin down. All right, so if we look at this, those 2 electrons will want to pair and form a new molecular orbital. When they do that, they'll form a molecular orbital called a bonding molecular orbital. And this bonding molecular orbital is more stable than the 2 of them separately, right? So I'll draw this bonding molecular orbital lower in energy, and it will be spin up and spin down. That will be our covalent bond that occurs between 2 hydrogen atoms. If If we think about this from a covalent bond point of view, we now have two hydrogens, let me even this out, that share that set of electrons. They're covalently bonded together. And they've got this electron cloud kind of going around them. It looks kind of like two s orbitals that are spheres getting close together, so it kind of becomes this oblong oval of electrons, right? That's our bonding molecular orbital. So let's label that. However, there's also a orbital that exists at a higher energy orbital or higher energy position, and this is referred to as our antibonding molecular orbital. This antibonding molecular orbital doesn't have any electrons in it right now, right? The two electrons are located in that bonding molecular orbital. However, if you excite this molecule with enough energy, you could actually knock one of those electrons from that bonding molecular orbital up to an antibonding molecular orbital. Doesn't happen very often, though, at least not with hydrogen. If we think about this antibonding molecular orbital, the orbitals look very different. In fact, you have a node in between the two hydrogens, so one node is opposite of the other. So this is a weird example where we occasionally run into it, especially when we get into higher level chemistry, but we're primarily concerned with the bonding molecular orbitals, at least as we're learning organic chemistry. Does that make sense? Okay, I'll assume it makes sense if everyone's quiet. But the reality is a little bit more complicated than this, right? Hydrogen's a nice simple example with only one electron in each lobe. Yep.
So they are still bonded in this case?
Yes.
Hydrogens are together?
Yes, the two hydrogens are bonded together, and they're sharing electrons in that bonding molecular orbital.
Just a higher energy state.
Yeah, there's a higher energy orbital called the antibonding molecular orbital. However, it's unoccupied, at least at a low energy state. In some or most cases, orbitals will hybridize. So that electron pairing can occur. So let's take a look at this example where we run into hybridization. And the example I like to use is methane. It's the simplest organic molecule. So it's CH4. We'll make our energy ladder. So I've got energy on the Y scale. We know we've got 1s, we've got 2s, and then we've got these 3p orbitals, so I'll call these 2p, 2p, 2p. Carbon has 6 electrons, as we saw previously, so we can go 1, 2, 3, 4, 5, 6. However, methane needs to make 4 bonds. Right now, we only have 2 possible sites where we could form a bond, right? So what we need to do is we need to hybridize things in order to come up with 4 possible unpaired electrons. And in order to do this, we're going to take all 3 of the p orbitals and that 2s orbital, and we're going to kind of mush them together into a hybridized orbital. Do you think the 2p orbitals will be higher in energy when we hybridize them or lower in energy? Yeah, they'll actually go down a little bit in energy. So it will stabilize our 2p orbitals. It'll drop their energy. We'll make our energy ladder. I'll try to put these down here. So we've got 3 p orbitals. that one s orbital, or sorry, the 2s orbital actually has to come up a little bit in energy because our hybrid orbital is going to be in between the two. So we've got our 4th orbital here, and then the 1s orbital is just going to hang out down there. It's not going to really do anything. So we've got 1s down here, and then our hybrid orbital, we took 3 p's, 2 s's, so we'll call that sp3. Actually, I'll just label it over here to save space. So these are now all sp3 hybridized orbitals. Again, we want to fill them from lowest to highest energy. So this 1s will go 1, 2, 3, 4, 5, 6. So by hybridizing that carbon, we now have the capacity to have 4 covalent bonds, right? Because now we've got 4 unpaired electrons. Each one of those electrons could bond with a hydrogen that also has an unpaired electrons. So let's make a little note of that. It's 4 unpaired electrons that can bond with the 4 hydrogens. All right, let's try to visualize this. It looks nice on a graph, but that doesn't really describe things three-dimensionally. However, we know a lot from VSEPR theory, right? CH4, what should the geometry be? Tetrahedral, right? So let's try to draw this a little bit. First thing we're going to do is look at the orbitals themselves. So the big question is, what do these sp3 orbitals look like? Well, we know it's a combination, let me make this bigger, of one s orbital plus 3 p orbitals that look like that. So if we take a sphere and mush it with a dumbbell, it becomes a lopsided dumbbell. So let's take a look at this. We've got one lobe that looks a lot like a sphere. It's a little oblong. And then this little tiny nub on the other end. So this will be our sp3 orbital. If we think about this, it has 75% p character and 25% s character. And we've got 4 of them, right? So we need to arrange these into a tetrahedron. So let's try to draw this. And in order to do this, I'm going to use a coordinate diagram. So we'll have x, y, and z axes. Oh. Just a second. This pen drives me nuts sometimes. I think I might need a new battery. Apologize. So we'll do our x-axis, or sorry, y-axis straight up and down. We'll do our x-axis kind of cocked to one side, and then our z-axis like that. One of these sp3 lobes could be sticking straight up, and there's a little nub on the other side. The other sp3 lobe we know is going to be one of the bar stool legs, right? So it's going to be kind of pointed down, have a nub back there. The other one's going to be kind of coming towards us. So it'll look like that, have a nub back there. Let's try to shade it, give it some perspective. And then the last one's going to be kind of sticking behind. Let's see if I can draw this. like that. So I'll give it a little bit of shading, and we'll have a little nub over there. A lot of people ask me, do you need to draw the nubs? That's okay, just do your best. So all of these are sp3. We know we've got one electron in each of these 4 sp3 orbitals, so I'll draw one electron. They're organized as a tetrahedron around that central carbon point. And then hydrogen we know is in an s orbital. And we're going to have hydrogen bonding with each of these lobes. And that hydrogen will contribute one electron to each of these lobes. So the hydrogen electron needs to be spin paired down, spin paired down, spin paired down, spin paired down. And the overall shape of methane will be a tetrahedron where there's an s orbital from hydrogen overlapping with an sp3 hybridized orbital coming off of carbon. All right, I think that's where we're going to leave things off today. Tomorrow when we come back, we're going to look at double and triple bonds and the hybridization that occurs anytime you have a double or triple bond. If you guys have any questions with the problem of the day, don't hesitate to stop by my office or ask a classmate. It's a really good idea to start your sapling problems as well. That'll help you get going as we get a little further into the chapter.
Oh, what's the